Okay, so this is the agenda. So a background summary, feature selection engineering, the training methods, the important findings, a simple model and code review. Let's start off with the background first. Okay, so let me see. Oh, I run this. Okay, this.
It might be. It's fine. This view is fine.
Find the full screen button.
It might be disabled.
Oh, first thing, I think it's bottom right.
Bottom right, yeah, but
Yeah.
it's,
If you go to the left, it's right next to the minus.
Oh, okay,
sign.
okay.
Yeah.
Okay. So basically, I mainly deal with computer vision. So, but I mean, computer vision is now also deep learning. So basically, what I've done before is identify factor in X-ray images. So I involved in robotics navigation, implementing visual SLAM. So currently, because now it's everything's generative AI, so I'm fine-tuning LLM models. Basically, I have a contract freelance programmer engineer. So I'm familiar with deep learning and build models in my work. So my previous Kaggle competitions, those involved in sequence modeling in molecules and medical application helped me with this competition. So for example, you have previously there's a molecular translation. So this is all these symbol image to the small formula. Okay, so we have the open vaccine. This is given the RNA sequence, so you predict the degradation of the vaccine.
Right.
Okay, so summary of my approach. So because
just a second, sorry.
Yes.
Your slideshow is actually not being shared with us.
Yeah.
You might want to just do it from your PowerPoint window.
Yeah,
That's
that works.
I think full screen is disabled. Okay, so okay. Let me see, I can make it bigger.
Yeah, this works. This is fine.
Okay. Okay, next slide. Okay, so basically a summary of my approach. So basically, one problem of this, one big issue of this competition is that there is out of domain distribution problem.
Right.
So in order to combat this, I try to use example of different sequence model. So I used 3 kind of models. So the first one is a simple convolution 1D net. So for this, I trained 3-fold. So the next one is actually the transformer network. Okay, so this is a transformer network. So basically, it's quite straightforward for both of these CNN 1D and transformer. The input is actually a single character tokenization. Okay, then in order to capture what we so-called the combinations of characters, so I actually use a convolution embedding module. Okay, so after, the single character will pass through the NN embedding, then there's a convolution layer before I pass that into the transformer.
Okay, so this was a pure single character. So like if we had chlorine in there, it would be capital CL, and that would be 2 tokens, right?
Yes. Okay, I have it here. So these are all the
Perfect.
Yeah.
Okay, great.
Okay. Okay, let me go back. Then just for curiosity, I tried a new all these single state machine which came to be very good. So I have a single for member. Okay. Another thing is that to handle 98 millions, which actually is quite a lot of training data. So we use customized CUDA kernel, okay, from open source. So you have the fetch attention, you have the member SSM libraries. Okay, so basically that is solution. Okay, for training, my hardware is actually 2 NVIDIA ADAS A6000. So each with 48 GB ampere. Time from training one single fold is as follows. For the CNN 1D is the faster 7 hours. Transformer is 28 hours. The member is 36 hours. So these are the results. So I make, okay, the reason why I try, you may see that it's different for different network architecture because I don't have the time to train for the same fold. But after the competition, I make some post late submission so that I can compare with the same fold. So basically, if you look at fold 2 and fold 4, 2 and 4, so these are common. So you can see that the transformer has a better generalization. A better generalization. Okay, so this is the, okay, if you look at the non-share private, you can see that the transformer actually stand out. Okay, where else the rest are actually just a 0.05. Yeah. Okay. For locally, it's pretty hard to test because basically I find that how should I put it, if you use different building blocks, okay, I mean,
Yes.
if you use some building blocks for the training and another completely different set of building blocks for the validation, the result kind of flip-flopping. So I don't know whether it works or it does not work.
Yeah. We had a ton of trouble just trying to do the splits for the competition because some building blocks like bind really strongly, others don't. So like depending on where they end up in the trainer or the test, you get very, very different results.
Effects, yeah, the effect is actually very pronounced for graphical networks. They are very brittle. Yeah. So I can't have a local validation set. So what we do is that we train for a few iterations and we verify, we submit and verify on the leaderboard. Yeah. So this, I think most of the people do. Okay. So for the next slide. Okay. So tokenization. Actually, I try a few tokenization, including those like the byte pair encoding.
Right.
Also tokenized according to the SMILES formula. So for example, CA, 2 character is considered as 1 token.
Right.
Okay, then surprisingly, the simplest character-based tokenizer perform the best. Yeah, it's actually much better.
This is something we've seen consistently. Like the simpler the tokenization, like the better. Like the byte pair encoding actually always seems to lag behind. And then like we've also heard from other groups that just simple tokenization is best.
Okay, for this maybe I can explain later in the heat map, the class activation. I do see some pattern. Okay, no, the surprising thing is that the atom aware tokenization actually does not perform better because CA is always together.
Right.
Okay. Yes. Then okay, the addition of the conversion layer to learn the consecutive tokens like bigram, trigram, this layer actually is effective. So if I remove this, the result actually is slightly worse. Okay. And one thing is that what I try is that since we are doing character based, we can do one hot encoding.
Right.
But that doesn't work. The embedding layer is required. That means, it's a lookup table. I think the reason is because if we use one hot, you probably need a few layers to have the same effects as the lookup table embedding. And maybe because of, it's very strange that your data training is not the same as your testing the OOD. So it's maybe difficult to learn. I'm not sure, but it's surprising that one hot encoding don't work as well. Yeah, so this is a surprise for me. Okay, then for batch normalization, okay, I find that the CNN 1D is very sensitive to batch normalization. For the rest of the sequence model like transformer, they have their own L2 norm. So, okay, this I guess this is due to the different feature values for the in distribution, out distribution, and also the class imbalance. So your positive and negative input actually have different feature value. So your batch norm, whether you norm to which side, so it's sensitive. So what we do is that we use pretty high EPS and also low momentum. Okay, next. Let me see. Okay, training methods. Okay, so okay, for different architecture, actually, we use different learning rates. So for the transformer member is 1E minus 4 minus 5. For the CNN is minus 3 minus 4. So because of the large amount of training data, so I don't use scheduler. So what we do is that we start from minus 3. So I let it train until it overfits. Okay, then from all these safe model, because I save it all at each approach, I choose the point where just before the overfit occurs, then I stack the learning rate and resume training from that point. Okay, my batch size is pretty large, so it's
How did you get a batch size so big?
oh okay.
We're struggling to get to like 128. Like
Okay, if you look at my model, they're actually pretty small. One thing is that they're pretty small.
okay.
Okay. Because I find that the deep model don't help at all. So you see 4 layers. So this one is let me see how this one. This one is also, this is 4 layers, this is 7 layers. But they are very small. They are really very small. The dimension is very small.
Sorry, how many layers did you have of the transformer?
7 layers.
Okay, so got it. Okay.
But it's 512. Okay, it's 512. And there's a fresh attention, all these that make it very memory efficient. Squeeze to 48 GB lah. I basically use out the 48 GB.
Yeah.
In my memory, yeah. So I try to adjust the layers, okay, and the dimensions such that I can get very large batch size. Okay, so okay, this is something also interesting. The best thing to handle this class imbalance is to do nothing at all, rather than have very large batch size. Okay, so same table. So okay, I am interested to know why transformer is perform better. So I selected some samples, so ABC. Okay, so basically what these graph? These are the correlation. Okay, you can call this correlation plot, or basically it's just a plot of the prediction probability of the x-axis is the prediction from the CNN, the y-axis is the prediction from transformer. So they are quite the same. Okay, this is, let me see. Okay, this is positive sample, this is negative sample. So I selected some point. Okay, C is transformer perform better, B is CNN perform better. Okay, A is everyone perform good. Okay, then these are the CAN map. Okay, point A. Okay, point A is everyone is good. Okay, so top and bottom. Top is CNN, bottom is transformer. So basically they have the same focus. Can you see? Okay, the thing is that okay, because of the way I use the transformer is still average pooling, not the CLS token pooling, is average pooling. Okay, I find that the value actually is very spread out. I mean, those which token actually has high response. Okay, so it's very well spread out. So you look at the CNN, right? You can see that there's some zero in certain place, and they're kind of looking at specific groups. Okay, but for transformer, you don't have zero value. Okay, and you can see that this has a larger area, larger region, I would say lah. Okay, reason why they really perform well is because the activation actually are just nearby atoms. Okay, you can tell from this, the stronger actually is nearby. Because I'm not a chemist, so I'm not sure whether this makes sense or not. Okay, but that's how the results show. Okay, then for C is where, let me see if I remember correctly. C is where transformer perform better. Okay, so I'm not sure whether this is right or wrong. So CNN capture this part, where the transformer actually capture another different parts.
Right.
Okay, so this is, so when transformer perform better, it's actually capturing different parts.
And so I see that you stripped out the dy in these representations, replaced it with a methyl. Is that how you did all your molecules?
Pardon, can you repeat your question?
You got rid of the dy.
Oh, dy, yes. not much or different actually.
Okay.
Yeah.
Well, so okay, great.
Yes. Okay, this is where CNN perform better. So when CNN perform better, transformer is actually all zero. Okay, this because all zero, so I don't plot. So when it perform better, CNN perform better is some very small area. Okay, some very small area. Okay. So as I'm not a chemist, I'm not sure whether it makes sense or not. So, but anyway, these are the results. Yeah.
Well, and it's a parenthesis, right? So it has like almost no physical meaning. It's just
Yes.
it's just how things branch. So,
Okay. So I mean, so conclusion is that transformer look at groups.
Right.
CNN look at small parts. Okay, so if you hit it, then you're right.
Right.
Okay, so that's why transformer generalize better because it actually look at groups. Okay, simple model. So this is quite straightforward because the results show that just using transformer actually it beats the example. Okay, this is surprise. Okay, for me. So I can actually just run the transformer. Okay. Okay, code review. Okay, this is quite straightforward. So I have it at the GitHub. So if any issue, you could actually send me email, can raise the issue there.
Great.
Okay, so basically okay, so these are the link to the Kaggle where there are more information. Okay, so these are hardware. Okay, so I haven't mentioned the CPU. Okay, the CPU is actually also important to process the data. So I actually have 24 core, 48 threads, and it's a 256 GB. Okay, the OS is Linux Ubuntu. So setup environment. So basically, you can just look at this. Okay, so this is the Kaggle data. So okay, it takes quite some time to pre-process the data. I have it at my shared drive, so you can download. Okay, so in order to pre-process the data, you just need to run this script. So basically, they tokenize it. Okay,
So you save the tokens and load the tokens directly into the model.
Yes. So it speed up my training as well.
That's probably the difference from what we're doing. Yeah.
Okay. Oh, okay. There's one thing I haven't mentioned, but I mentioned in the discussion. Okay, the thing about having because you got 98 million molecule. So if you use PyTorch, because of the I have the link in the discussion as well. So you got any question, can send me to email. Because PyTorch use Python multi-processing. So for some reason, when they put into the queue, the queue itself, the processing queue is a memory copy. So one airport, so many molecules, so it will keep the memory will keep on increasing until the end of the airport. You will release all the memory.
Right.
That is why I do not use the PyTorch data. Sorry, I do not use the PyTorch data loader. Correct. I use indexing.
I see. Okay. We are using the data loader. So
yeah, I think that improved my memory a lot. Okay. Then so this is a path modification. There's only one file you need to modify. Okay, for training, okay, I have it all in a one file called run train. Okay, one train. So okay, this one run train. So if you execute this, it will just save all this file. It will produce all these file. Okay, if you look at that this Python script file, it will be something like setting out the CFG file. Then you enter the parameter. Then you call a function called run trainer. Okay, then it will set out the CFG file again, which then you input the previous checkpoint, resume point, then run trainer. Okay, so it's a sequence of these two statements. Okay, if you want to do local validation, I have it here as well. Just run validations. All this will save in the log file. There's a train log file, there's a version log file, and all this can be downloaded from my Google Share Drive as well if we want to compare the results. Okay, as for the submission, then there's a run submission. So you will get this. So I have it for the single submission and the combined submission example. Okay, then so this is a shared drive, which you can find all the weights, train weights, and the box files. Okay, I think that's all. So if you've got any question, you can ask me.
Right. How did you represented the protein in that, like, you just have 3 separate tasks?
Yeah, 3 separate tasks.
Okay, great.
Yeah.
So yeah, we definitely ran into these issues. Yeah, we're trying to predict out of distribution, right? And like, you know, at the end of the day, this is a physics problem, right? These are physical molecules on the same kind of proteins. Like, there should be some representation of like the shape of the protein, like that it should be able to like generalize to the physical system, we think, right? What do you think?
Okay.
What were the problems of this data set that made it so we couldn't do that out of distribution?
My suggestion is, why don't you take your data set, do all these prediction of this molecular property. So you know that there's some open benchmark like QM9, QM. I mean, predicting some, don't know what.
QM9.
Yeah. Okay. I don't know what QM9. Okay. Anyway, there are a lot of molecular data set. They're pretty molecular property, correct?
Well, but those don't generalize either, right? So this used to be my job at Recursion, was like training models on the open data sets and then testing them.
No. Okay, you let me finish. No, it's not what you think. Okay, at least we proved that for this open data set, they can generalize for their molecular property. All right. So so what we do is that if for our data set, so you also compute the ground truth of this molecular property and see whether your validation and your test, so your test, your hidden test and your public train, you can use your train to predict the molecular property of this. If the answer is yes, then there's no problem with all this method you read from the papers, because they does work. Then the problem is the protein.
Sure.
Yeah, but I'm suspecting that probably the molecular property you cannot predict. So if you cannot predict the molecular property, it's just so that your molecule structure wise, they are not the same, or they're not the same as the public data set. Although you got so many training molecules, okay, you need to aware that your molecule is synthesized from blocks. They are not, they're actually not generalized. Yeah, so I think that's an issue.
So you think if we trained on if we had more building blocks available?
Yes. So it's not the number of molecules, it's the number of building blocks.
Right. Yeah. I think we agree. We just moved to a new library that's only 2 cycles and about 20,000 building blocks. So we're hoping that helps with it.
Okay. Again, based on what I discussed previously, you can estimate the molecular property of the building blocks.
Right.
To see whether they overlap or not. Yeah.
Okay.
Yeah.
And then at what point do you think having multiple proteins would actually be useful?
Okay. If you want to use multiple protein, then it will not be a virtual screening of molecular property problem. It become a drug target interaction.
Right.
But again, you need to build this cross attention disk. So assuming that you solve the first problem such that, okay, I'm able to predict for these 3 target protein well for my test. Then I introduce some protein, okay, which is not used in training, okay, but I know that this protein is similar to these 3 protein, so I expect they have the same result.
Right.
If I do this test, it says that, okay, even this protein is unseen, I get the same result. Okay, then you probably don't need protein to train, but I don't think this will happen. Okay, then you can measure the affinity of this new protein with these 3 protein. You should see your results start to degrade when the affinity decreases. Okay, if that is the case, then by right, if we train with new protein, the result should improve.
Right.
Yeah. So basically, you have the protein space and you have the molecule space.
Mhm.
So we need to know where our data actually lies.
What if we were to do this competition again?
Yes.
What do you think the shape of the data set should be? So
My
like,
okay, even for this conversation again, I have a suggestion. Okay, why don't you hold it a very long competition, 1 year,
Mhm.
with very high price money, where you still get your hidden data, you still can have your strain data,
Mhm.
and you allow people to collect their molecules. You give them a way so that they can do their DLE or whatever. They will figure out how to solve your OOD.
Sorry,
Yeah.
they would collect their own data, or
Okay, they have the option to do that, or they don't have to. So you provide your data, lah. Okay, you provide your data,
right?
but because it's an OOD problem,
Uh-huh.
and it's 1 year, so if they feel that they need more data to solve this OOD,
Uh-huh.
It's up to the participant to collect their own data.
I see.
Okay.
Well, I mean, we would
okay.
love people collecting data here.
Yes. Okay. Because I'm new DLE lah, so basically I need to do a lot of background search. So I actually read a few company how they actually market their product or how to use their product. I can't remember the company. I think it's Wuxi or another company. What they do is that they actually send free kits, DL kits to institutes. Then for the exchange that if they return the result back to them, they will do the analysis for them.
Right.
Something like that. So you can do something likewise. I'm not sure whether you can have a dry lab version.
So, but then you start dealing with batch effects between different labs. So like, different labs run the experiments slightly differently, or another issue with Wuxi is they don't report all the molecules, they just report your top hits. So
yeah, okay, but let's say if you do it from a competition point of view, so the participant objective is not to do drug discovery, is to solve the OOD problem.
Right.
Yeah, but how to design such a kind of competition framework where you encourage people to collect their data?
Well, we think you're going to be collecting the data, right? So like we create our own proteins. We can do 200 a month. And we can screen those against large libraries. So like we're trying to figure out like what is the winning data set to solve this problem look like? And right now we're kind of seeing we kind of learned that like, okay, we need more building blocks, definitely.
Yes.
So we went to 2-cycle libraries just so we could get lots more building blocks out. They were quite a bit more expensive because you have to buy all the building blocks.
Okay.
But then we also think like actually your example with GradCam was great. Like looking at the different models, how the convolutions were really focusing in on particular atoms. Right. We think that this is like a general issue where the models just kind of memorize chemical motifs. And that's really easy for them to do. And it makes good progress in the validation or in the training set because there's a few building blocks you just need to memorize. So our hope was that like maybe by moving to more proteins, the model would have to pay attention to both the protein and the molecule and like how they could fit together. So that's kind of the bet, and we're hoping that like we're gonna get 500 proteins by the end of the year, and we're hoping that that's gonna start moving us in that direction. Because then we can start like sampling sparsely, but we don't know, right? This is the big bet.
Okay, I have 2 more comments lah. One is that for the next competition, if you want to organize, maybe you can see that for this one, there's as the competition runs, right? You can see that Kaggle start to point out the issue with your data set and other things. So I'm not sure whether Kaggle can do it in such a way that you have a trial run first. for people to try to find out issues.
Right.
Then you, or maybe, okay, I don't think this work, but maybe a group of Kaggle to run the competition, try run the competition first. I think you need to open to all. That's why maybe it's 2 stage. Because the trial run first. Okay, so that's one comment. Another comment is that, okay, if you're talking about generalization, okay, because I'm not a chemist, but I think that actually, if you can predict some electrostatic or some probability related to the bonds, that means your model can predict all these energy values. In that case, that should make the model generalized, correct?
Maybe, but like the problem with a lot of those
Yes.
property predictions is like either they're measured and they're coming from many different labs, and you're like really biased by like which labs are reporting which molecules, or they're calculated by a computer.
Okay.
They're already an approximation, and there's already a formula to calculate them. So like, you could actually just write out an exact formula to calculate a lot of those properties.
Okay.
So it's not as interesting a task.
Okay, I get what I mean. Because my concern is that from molecule to affinity is if you can find something in between, okay, something in between, then maybe it works out.
This is, you know, I don't know if do you follow AlphaFold? What DeepMind is doing with AlphaFold at all?
Yes.
So that might be an in between task, right? Like basically their thing is given them, you know, predict the pose given that the molecule binds.
Okay, but the thing about DeepMind is that part of success of DeepMind is because they have a database at the back. Okay, I mean they want to fold the DNA, right? They have a database at the back, so they have a very good initial experiment. Initial solution.
Yeah, I mean, I don't know that they have that much data. I think they are mostly just using PDB bind. And
okay, this I'm not sure, but they have the initial good. So no, actually, I'm wondering that if DeepMind started just pure transformer, I don't think it works. They need the initial solution first. Okay? But then after that, they can use AlphaFold to generate a lot of solution. Then they can start from scratch from transformer.
Okay, that's an interesting idea.
Yes.
Did you look at any of the pose prediction models at all? Did you look at training? Training on like PDB bind or pose busters or anything like that?
No. Okay, actually, I haven't mentioned. I also tried 3D.
Right.
I mean, all the conformers stuff. Okay.
Which are a pain to generate, but
yes, the results are not better.
Yeah.
The results are not better. Then I give up. Yeah.
In the past, we ran into a company that was using the conformers to make predictions, but we found that their model did just as well if you shuffle the 3D information across all the atoms.
Oh, okay. So does it mean that all these all these docking software that it doesn't work at all? This has been a mystery for me.
We were really we were hoping that there's a bunch of people making big claims about docking. We were hoping that they would compete.
Yeah.
But I guess the validation set was too big for them, or they didn't want to get embarrassed. So like we didn't see very many people trying docking at all, which was very disappointing for us. We made the validation set out, down the full thing downloadable just so the docking people could take a swing at it.
For my case, that I don't have enough knowledge to do the docking because I tried. I find that you still need some expertise to know what to do. Yeah. So okay, but the question I want to ask is that does drug company actually use docking to prove that it works before they go to the wet lab?
Yes, they do, but no one believes it.
No one believes it. Okay, if docking really works, let's say it really works or to some extent, for the next competition, okay, you can have a package where if you want to dock, okay, then you have more train data. So
Yeah,
you
so
leave
docking tends to work if you have
Yeah.
a very, very similar molecule
okay.
that was also docked, that you did. If you take an X-ray crystal of a very similar molecule
Okay.
to a
Okay.
very similar protein, you can kind of make docking work, but it's still kind of
Okay.
been looking at it and throwing out 10 of them and picking the one that they like the best.
Okay. Okay. I get it. Yeah.
So, and we have a medicinal chemist here who basically does that a bunch, right? He will design a molecule, dock it, and then tweak it a little bit and see what it does. But we haven't seen people really try it, and we hope that people will. That's why we're releasing the data after the competition so that hopefully someone will try dock.
I think data is not enough. You need to have a working notebooks.
Yeah.
Yeah.
We're talking with some people at NVIDIA who have the compute, so hopefully they'll sit down and do it.
Okay. Okay.
Yeah. Anyway, do you think? Yeah. I mean, it's great work. We loved watching you. Like, we loved how much you shared everything. That was awesome. I think we all learned a ton from you.
Okay.
Steven, do you have any questions?
I think you pretty much answered. You pretty much asked all the questions that I had, and then I just want to say thanks so much for like all the contributions to the competitions. I learned a lot from that too.